Very sensitive. All right. Okay. You guys over in Enid's can see the document camera? Thumbs up? All right. Okay, so the problem, which is the one that we have a ball that's being tossed directly up, and it's coming back down, and it's going up at 19.6 meters per second, and we're asked to find the average velocity. Okay? So remember, velocity is going to be change in position versus the change in time. I start here, so this happens to be at 0. I finish here, it happens to be at 0. So if my position final is 0 and my position initial is 0 divided by whatever time it is, doesn't matter. The answer is 0 meters per second. So the answer was not given, because they all had different numbers, right? Remember, when I'm doing displacement, displacement is a vector. The displacement is a vector. So if I go from here to here, it doesn't matter whether I went there to there to there. My displacement vector is that right there. It only cares where I stop, where I started. So the other thing you could have done is said, okay, let's just do a direct average, my velocity average. If I was going here, I'm going up at 19.91, or up to at 19. My final one was at minus 19.6. My average is still, my change in velocity was equal to 0. I could have gotten it that way as well, because that would have been the two velocities. I would have had my minus 19.6. I ended up adding, I would end up subtracting, because they're going different directions. So my change is 0 divided by 2. It's still going to be 0. Right? Because I'm not changing. My displacement is a vector. Velocity is a vector. Acceleration is a vector. All of them are vectors, and vectors have direction and magnitude. Okay? So let's look at another one, very similar. I'm going to use white paper this time. All right. So I'm standing on a cliff here. Standing on a cliff. We're going to toss something up, and it's going to... Things we know. Okay? Things we know. Things we know are, I have a set of kinematics equations. I have the velocity final is equal to the velocity initial plus the acceleration times time. I have velocity final squared is equal to the velocity initial squared plus 2 times my acceleration times my change in position. And I have my change in position is equal to my initial velocity times time plus 1/2 the acceleration times time squared. So I've got that. Without even reading the problem, if I'm tossing the ball straight up and straight back and it's coming straight back down, what's my acceleration that I'm experiencing?
Gravity.
Gravity. So I know I've got gravity going in that direction. Okay? We know probably we have an initial velocity, and that initial velocity is going up. I know the velocity at the top. What's the velocity at the top?
0.
0. So I know that. Things I may or may not know, or may be asked. I may be asked the height. Okay? I may be asked this height. I may be asked this height. I may be asked for time. For velocities at various points. And I may have to figure those out. But one of the things I do know is that because of symmetry, this velocity hit this point and this velocity, it's going to be the opposite direction of the. Now, that's if I'm in one dimension. That's if I'm in one dimension. I can have something similar where I'm in 2 dimensions. Still have gravity, but in this case, I have to worry about the fact that I have a velocity vector. And I'm going to draw this over here so you guys can see it a little better. I have a velocity vector, and my velocity vector is going to have some sort of angle, and I'm going to have a velocity in the x direction, and I'm going to have a velocity in the y direction. So if I have this angle, I'm going to have to count velocity in the y direction. That's going to be equal to my initial velocity times the sine of my angle. This is going to be the initial velocity times the cosine of my angle. Question is, what's the acceleration in the x direction? What's my acceleration in the x direction? If I toss the ball, what's my acceleration in the x direction? Do I have anything providing my ball an acceleration in the x direction? Do I? Once it leaves my hand, do I have anything providing me an acceleration in the x direction? Okay, so let's look at what happens with my hand. So I'm going to get my hand here. The ball leaves my hand, and once the ball leaves my hand, is there anything that is pushing it or pulling it in the x direction? Okay, I think I heard it. Do I have anything pushing it or pulling it in the x direction?
No.
No. I have nothing. So acceleration in the x direction is 0. When I'm doing something like this, once it leaves my hand, I have nothing that's causing an acceleration in the x direction. I only have an acceleration in the y direction. So because my x and y are independent. So when I have this situation where I've tossed it over in a distance, I have nothing that's causing me an acceleration there. Nothing's pushing it, nothing's pulling it, nothing's getting me. That is different than when I have this situation. So I've got my little Dr. Seuss car here. And it's going out there. We're going to say it starts with a velocity of 10 meters per second. Okay? And we've got a traffic light up here. And it's now yellow. I don't advise this, but how many people do it, right? don't advise this. And we are going to travel 50 meters. Okay, we're going to travel 50 meters. And we're going to say it takes 2 seconds to go from yellow to red. If I want to make the light, what's my acceleration got to be? I want to make the light, what's my acceleration got to be? Okay, so let's look at what I've got here. I've got an equation that says that V final is equal to V initial plus acceleration times time. In this case, I do have an acceleration in the x direction because I've got something that's going to allow me to accelerate. I can push my foot on the accelerator pedal, so I can accelerate. So I can do that. So I've got V final squared is equal to V initial squared plus 2 times my acceleration times my change in distance. And I have a change in distance is equal to my initial velocity times time plus 1/2 AT squared. So let's look at what I've got. Do I have the final velocity? Yes or no? Come on, I know it's early. Do I have a final velocity? No. We don't know that. So I don't know final velocity. So, that's going to cause me a problem. That's definitely going to cause me a problem. Do I have a distance? Yep, I got a distance. And I have a time. So this one requires final velocity, so I can't use that one. This one uses final velocity, so I can't use that one. So that leaves me with this one right here. I have a distance. I have an initial velocity. I have time. I'm trying to find acceleration. So I can do that. So I'm going to do distance is equal to my initial velocity times time plus 1/2 AT squared. I'm going to rearrange this to solve for A. So I'm going to have my distance minus my initial velocity times time is equal to 1/2 AT. So I get 2 times my initial velocity times time. I'm going to divide both sides by t squared. That's going to give me my acceleration. So let's plug in the numbers. So I have 2 times my distance is 50 meters. Minus my 10 meters per second times my 2 seconds. And I've got 2 seconds squared down here at the bottom. So acceleration is going to equal 100 minus 20. My seconds cancel. This is meters on top. That's good. And I've got 4 seconds squared on the bottom. So I've got meters per second squared, so I know I've set up my equation right, because I've used my units to help me out. So I get 80 divided by 4. And so I'm going to have, and this is meters per second squared, I'm going to have 20 meters per second squared acceleration if I'm going to make the light. Again, I don't recommend it. We don't like flashing orange lights. It's not safe, but we can calculate it. So that's different than when I have 2 dimensions, because in this case I have nothing that's pushing or pulling the ball once it leaves my hand in the x direction. I do have something pulling on my ball when it leaves my hand in the y direction, and that's gravity. So let's look at another situation a little bit. So I have a situation here where I've got a ball that's going off at 2 meters per second off the edge of the table. And I drop a ball over here at the same time. So these are at the same time. This is 1, this is 2. which ball hits the ground first? I'm going to give you three choices. Ball number 1 hits the ground first. Raise your hand. Good. Ball number 2 hits the ground first. Raise your hand. I got a couple hands. They both hit at the same time. Raise your hand. I got a bunch of you didn't respond. They both hit at the same time. Because they're both experiencing gravity. This one had a velocity in the x direction only. The velocity in the y direction for both of these balls is equal to 0. So there was nothing that was going to have one ball hit the ground before the other one. They're both going to hit the ground at the same time. Now, where they hit the ground is a little different. If I were doing this precisely at the edge of the table, ball 2 is going to hit at the bottom, ball 1 is going to go off and hit a target someplace over here. And we can figure that out. Because I can use my x and my y to help me figure it out. I can use my y to find the time. Because I need time to figure this out. So if this is 0.9 meters, okay, it's 0.9 meters to the top of the table. My y is going to equal my initial velocity times time plus 1/2 at squared. I have no initial velocity in y. So now if I'm going to rearrange this, I'm going to get 2y, except my y is in the negative direction, because if this is 0, this is going to be in the negative direction. Divided by gravity is equal to time squared. My gravity is negative, so that ends up being positive. So I'm going to get time is going to equal the square root of 2 times my 0.9, and that's in meters, divided by 9.8 meters per second squared. Meters cancel. I'm ending up in seconds squared, so I know I've done my arithmetic correctly. So if I do 0.9 times 2, divided by 9.8, take the square root of it, I get 0.43 seconds. Now, if I look at my equation here, x is going to equal the initial velocity in the x direction times time plus 1/2 at squared. But I have no acceleration in the x direction. So I know this is 2 meters per second. I did it at 0.43 seconds. And it's going to tell me it lands 0.86 meters. Seconds cancel. It's going to out here. Now I know Tonkawa's already done this lab, right? You guys did this lab this week? Off the ball going through the 2 photo gates. I don't know if you guys over in Enid have done it yet. But this is exactly the problem that you've got. And it's because x and y are independent. X and y are independent variables. This is the same problem. This looks a little different. If I have my little Dr. Seussian plane and I'm dropping a package off, it's the same problem. It's not any different. Heights are different. All right, so let's look at vectors a little bit. I've got a soccer player. And my soccer player is going to start, so I'm going to draw kind of a little picture picture here, and we're actually going to draw it to scale. My soccer player is going to start here at the corner, and it's going to run this direction, and then we're going to make a turn, and we're going to make a turn kind of that direction. And what we're doing is this one, we're going to run 65 meters at an angle of 33 degrees, 33 degrees from the end, okay? So basically what I'm doing is I'm giving you this angle. Then we're going to make a turn. Oh, and the time that this took was 8.3 seconds. So the run for 65 meters is going to take 8.3 seconds, and it's going to be at 33 degrees. We're going to take a turn, and the turn is going to be a 25-degree turn from the vertical. And we're going to run another 20 meters in 3 seconds. I want to know a couple of things. I want to know, okay, I want to know the change in displacement, so I'm going to write this out, the change in displacement. I want to know the average velocity. And I want the final vector. And this time I brought a handy dandy protractor. So we can actually look at this and show how we can do it graphically rather than in its algebraic form. And then I'm going to do it in its algebraic form. So we're going to do it both ways. Okay? We're going to do it both ways. So I'm going to use a scale of 1 inch is equal to 10 meters. So I'm going to draw my, hopefully I'm going to draw my endpoint here. And we said that our soccer player is going to go from 33 degrees. Okay, so there's my 33-degree line. And I'm using 1 inch is equal to 1 inch is equal to 10 meters. So I'm going to be on that line. There's my 4-inch mark, and I've got to add 2 inches there. So there's my, oops, that's 2 inches. I want 65. There we go. There's my 65. Okay, I've got soccer players in here. Got a soccer player somewhere, right? Do I have a soccer player in here? All right. What's the end to inside of the from one sideline to the other sideline? What's the distance? 110. 110? Or end to end is 110, isn't it? But and what's the sideline to sideline? About what? How many?
About like 50 yards.
Is it 50 yards?
Ours is like 60 or 70.
So it's like 60 yards, so it's about 60 meters? Because I'm going to find out if I have somebody run off the sideline. I didn't calculate that. I didn't calculate whether or not he actually went out of bounds, okay? I didn't calculate that part. But we'll figure that out here in just a second. So there's one vector. That's the first vector. Now I said in the second one, the second part of it was, and this is when you start having to distinguish what the question is asking. So it says that we went 25 degrees from the vertical. So I'm going to actually put my little handy dandy protractor here. And I'm doing this graphically. I'm doing this graphically. And we want 20 degrees from the vertical. Or 25 degrees from the vertical. 10, 20, 25 degrees from the vertical. It's right about there. And I said it was 20 meters, so we only need 2, but I still need my line. So there's my line. So I can actually put in some information. There's my 33 degrees. Here's my 25 degrees. So that's how the person ran. The resultant vector, if I'm doing this graphically, because I want to be nice and neat, everything, because I add vectors head to tail. That's my resultant vector. Okay, that's my resultant vector. And we can actually measure that. So if I do that, I can actually measure it. And if I do this measured, take my handy dandy protractor, measure my end here. That's 4. It's a little over 7. Okay, it's a little greater than 7 inches. So it's about 70 meters if I do it with my scale. So we're in meters. And if I do my measurement of my angle, because I can do that, I'm at like 49-ish, about 49 degrees. That's the way I did it graphically. All right. So if I do this, and I want to look at, and I'm going to actually do this in terms of black so that we have it, I can do my X and Y components. So this vector here, this vector and this one is going to be of my 33 degrees. And when I do that calculation, I get 54.5. So if it's a soccer field, we're out of bounds. But if it's a 60-meter wide soccer field, we're still in bounds. We're getting close, but we're still in bounds. If I do this side, this is 65 sine of the angle, 33 degrees, and 35.4, and these are in meters. So if I'm at about 110 from end zone to end zone, I haven't quite made it to midfield. But now I got to do this other part. Now, if I do this components for this vector, this is going to equal, because this is 20 meters, this is going to be 20 times the sine of the angle. And if I do that, I get 8.45 meters. This one right here is 20 times the cosine of the angle. And that equals 18.13 meters. All right, remember when I was showing you triangles, there's my angle, this is the adjacent side, this is the opposite side, that's the hypotenuse. Cosine of the angle is the adjacent over the hypotenuse. So if I'm doing this, I get the hypotenuse times the cosine is going to give me the adjacent. That's why I used the other angles here. Did I do that right? No, I wrote these wrong. This is not the sine. This one is that side. This one is that side. This one, because this is the opposite side, this one is the adjacent side. All right, so we've got those straight now. I've used this 25-degree angle to get those straight. So I'm going to keep our picture handy. And I'm going to write out my vectors here. So vector 1, so this is the run 1, is going to equal 54.5 in the I direction plus 35.4 in the J direction. Run 2 is going to give me negative 18.3. Nope, writing it backwards again. Going to give me positive, or my y is my positive 18.13 in the J direction, and I've got a negative 8.45 in the I direction. Because here's my second vector. This is in the negative direction. This is in the positive direction. This is my y. That's my x. So now I have it written out that way. So I can add the vectors for my resulting vector. I'm going to get 46.05 in the I direction. And I'm going to get 53.53 in the J direction. So doing it arithmetically, where I've used my symbols, that's what I've got. To find the magnitude, I'm going to take a squared plus b squared. In this case, my a squared is my 46.05. Let's square that plus my 53.53 squared. That calculator, and I get 70.6 meters. And when we measured that, we got about 70 meters. So I could do it graphically, or I can do it arithmetically. I can find the angle. The angle is the arc tangent of my y divided by my, I do that 53.53 divided by 46.05. Inverse tangent. Says it's 49.3 degrees. And I measured it at about 49 degrees. We can do it in pieces. And the whole reason why we do this is so that you can get your x and y components of your vectors when you need them. When we break apart the x and y parts of the equations. Alrighty. And you're likely to have problems like this on the test.
We have a question from Enid.
Sure.
You push the notes up.
Do what?
We can't see the bottom. You push the notes up. We can't see the bottom of the page.
This one?
Yeah.
That get you?
Thank you.
Yep.
Yes.
Okay. Yeah, it's always interesting how the different screens carry different stuff. Okay, so everybody's with me? So we did it graphically, and we did it arithmetically. So you can add your vectors head to tail. Okay. So I'm going to use a situation here. So we're going to draw our picture. The distance from the edge of the table to the wall is 2.5 meters. The height of the tabletop is 0.9 meters. And I'm going to use a pocket catapult. I'm going to use pocket catapult. And we're going to send our little ball with our pocket catapult. So we know it's going to have some sort of projectile motion situation. Over here. And we're going to send this off with an initial velocity vector. And I'm going to use an initial velocity vector to start of 9.3 meters per second. I just pulled that number out of a hat. I don't have any good feel for why that number would be the case, but I pulled that number out of the hat. And I want to know where the ball hits on that side of the room. Okay, I want to know where the ball hits on that side of the room. And the only other piece of information that I'm given is the angle for my catapult is 110 degrees. At least to start. So this is where I want to find. Okay, so the first thing we got to do is we got to look at our vector. So actually, first thing you do in any physics problem when you start, take out a piece of paper, draw your picture. Okay? So we've taken out a piece of paper, we've drawn our picture. Because our picture is going to help us out. Next thing we want to do, when in doubt, figure out your vector components. Okay? So when in doubt, figure out our vector components. So I'm going to draw my vector components over here. Here's my little catapult. And we're told that this is 110 degrees. And I can actually start figuring out my vector components because if that's a right angle, and we set up our catapult that way, that's a right angle, then this angle here has got to be what? Go back to your geometry. We've said that this is 110 degrees. This right here that's 90 degrees. 110 minus 90 is equal to 20 degrees, right? That means this angle right here is 20 degrees. If I do the whole thing here, I can do it a couple different ways. The black one is 180 degrees. So if I take 110 minus 180, I get 70 degrees. So that's one way to find it. Or I can use the 20 degrees to find it. And so this angle right here has got to be 70 degrees. Which means that this angle right here has to be 20 degrees. I can use some identities, and if I knew that that was 20 degrees, I could figure out that that was 20 degrees. So I've got 20 degrees. So now I'm looking at my velocity vector. And I can figure out its components because I know that angle. So if I do that, now subscripts really help you. Okay? V of x, V of y. I've got this angle, so I'm going to use the cosine of 20 degree angle, 20 degrees. My V naught by my problem is 9.3 meters per second. So my Vx, when I actually plug this in, I get 8.7 meters per second, and I get 3.18 meters per second, or 3.2 meters per second. Okay. That's going to help me out. So now I can write my equations down that I might have. I know that x is going to equal v of x times time, because I have no, once it leaves the catapult, I do have an acceleration due to gravity. So my y is going to equal, that's my initial velocity, minus gravity divided by 2 times time squared. Now this y is going to be in this direction, so this is my y direction, this is my x direction. I've got final velocity in the y direction is equal to my initial velocity in the y direction minus 2 gravity times the height. And I have my velocity in the y direction is equal to my initial velocity in the y direction minus gravity times time. Well, if I want to know this height over here, I kind of gotta have either the final velocity or I gotta have time. We use 2 equations. We got 2 unknowns, so we can actually start looking at what we want to do. But these are independent of the distance that I'm at. So I'm at 2.5 meters is equal to my 8.7 meters per second. I don't 5 meters divided by 8.7 meters per second, put seconds on top. And if I plug that into the calculator, 2.5 divided by 8.7 gives me 0.29 seconds. Okay, I could do this because my x and my y are independent, and I know the x distance it travels. Well, if I know that, I don't need this. I don't need this. This is going to give me my y. Okay, this is going to give me my y. So I'm going to do y is equal to my 3.2 meters per second times my 0.29 seconds minus 9.8 meters per second squared divided by 2 times 0.29 seconds squared times 0.29. This gives me 0.928, and I'm in meters, so that's good, minus 9.8, oh, I should do my 0.29 squared first. 0.29 squared times 9.8 divided by 2, 0.412 meters, 0.928 minus 0.412 gives me 0.516. Okay. If I plug this into WebAssign, I'm probably going to get the big red X. Probably going to get the big red X. Because the question asks, what's the height on the wall? When I did this calculation, essentially, my picture's a little off. What's happened here is my ball goes up and it hits the wall up here. Calculated is the 0.516, calculated this distance right there. So if I want to know the height on the wall, I have to add the 0.9 meters, so I'm going to end up with 0.9 plus 0.156, and that's going to give me 1.416 meters. And that's what's my H that I plug into WebAssign. And web assign finally says, yeah, you got the green check mark. Okay. So we can figure out where it hits the wall. I can also ask another question because this essentially is the basketball problem. Except now I'm going to just, instead of a basketball hoop, I'm going to have a target. And I'm going to tell you this target is 0.2 meters above this spot right there. And now I want to know what's the initial velocity that I have to have in order to hit the target. Because my 9.3 obviously is not going to hit my target. I got to figure that out. So same things apply. Except now I'm going to do a couple little different things. Because I don't know my initial velocity. This one we were given the initial velocity. Now I don't know my initial velocity. So basically what I want to do is my initial velocity or my velocity in the x direction is going to equal the initial velocity that I want to know, cosine of the angle. I'm not changing my angle. Okay, I'm not changing my angle, so this is going to be my initial velocity times the cosine of 20 degrees. My y is going to still be the initial velocity, sine of the angle, okay. I still have x is equal to the angle times my time here. I'm going to do the same thing I did before, so I'm going to get my 2.5 meters divided by my initial velocity cosine of 20 degrees. That's equal to my time. Now my change in y is equal to my initial velocity times time, but my time is now 2.5 minus gravity divided by 2 okay, and we know what that is because they told us we want to be at the target of 0.2 meters. So the only thing I don't know in there is my V naught squared, or my V naught. So the book will tell you to rearrange all of this and solve for your unknown variable. That gets cumbersome in this case because I've got kind of a mess, right? Couple things we can do to simplify this. That cancels out. And I get 0.2 is equal to 2.5 tangent of 20 degrees because sine over cosine is a tangent. I get 9.8 divided by 2. I get 2.5 squared. I get V naught squared cosine 20 degrees. If we want to check our units, that was in meters, so this is now in meters. That's good. This is in meters squared divided by meters squared seconds squared, because that's my velocity, and I've got meters second squared. Second squares cancel out, meter squares cancel out, and that is in meters. So my unit analysis shows that I'm okay there. So I'm going to rearrange and clean up a little bit. So I get 0.2 minus 2.5 tangent of 20 degrees is equal to minus 9.8 times 2.5 squared divided by 2 cosine of 20 degrees, 1 over V squared. And you can play with this and get it to something that looks like this. I get v squared times 2 cosine 20 squared. This is squared. Times 0.2 minus 2.5 tangent of 20 degrees is equal to minus g times 2.5 squared, which ends up being minus 61.25. V naught squared is this becomes 0.88. The cosine 20 becomes 0.88. You've got your 2, and this becomes a negative 0.71. Just if you want to play with it to get there. So you get a negative 125 V naught squared is equal to a negative 61.25. V naught squared is equal to 49. V naught is equal to 7. And that's in meters per second. So this just becomes a little messy in the end, but I can still solve the problem of figuring out that I have to have the initial velocity of 7 meters per second in order to hit the target. Now I think you have a homework problem. I just can't remember if I have assigned it, where I have a ship and we have an island, and we have a ship that's trying to hide behind the island here, and you're wanting to find a place where it just gets over the top of the mountain, and then you want to find where it gets closest to the mountain. So you're trying to find this distance, and you're trying to figure out if the ship can be out of range or in range. And basically what you're looking for are these two angles. You're looking for the difference in these angles. So it's a similar kind of problem, except now you're looking for the angle instead of its initial velocity. Somehow, I'm guessing brains are full. Yep.